Hi. So today we are going to solve a LeetCode medium problem, count good numbers. So let's go through our problem statement once and we'll see what we need to do here. So we are given a definition of a digit string, and a digit string is good if the digits at even indices are even and the digits at odd indices are prime. Now we are given an integer n as an input, which can range up to 115, and we need to find the total number of good digit strings of length n. And a good digit string is where the means the values at even indices are even and the values at odd indices are prime. So for example, if here n equals to 1, so we need to make one length digit string. Now at and since this is the 0th index, so that means even, so we can only fill even values here. So the even values possible are 2, 4, 0, 2, 4, 6 and 8. Hence there are 5 possible ways to fill this position, and there will be 5 total number of good digit strings for n equals to 5. Hence the output is 5. Suppose for example n was 2, then in that case this is the 0th index and this is the first index. So number of means we can fill this position with 0, 2, 4, 6 and 8. And since this is an odd index, we can only fill prime values here, and the prime values, digit prime values are 2, 3, 5 and 7. So hence the total number of means total possible ways will be to the multiplication of number of choices we have. So it will be like 5 into 4 equals to 20. So now since here as you can see, constraints of n is really high. So if we try to think of a recursion approach to solve this question, recursively fill these values and then move the index ahead, call um, recursion function for a index, then if at a given index we will try all choices. So either like index even, then we have 5 choices, and index odd, then we have 4 choices, and then we will call the recursive function again for index plus 1 and so on. So since at each step we have multiple choices for this problem, the complexity of this problem would be since every two step we are having 5 into 4 choices, so it will be like 5 into 4, and total n steps we need to move, so uh, n by 2, since we are accounting 2 steps at a time. So the complexity would be of the order of 20 to the power n by 2, and since n is of the order of 1e15, so that means it will be of order like 20, so root 20 to the power n, so something like 4.7 ki power n, and which is really high, right? So we cannot solve this problem recursively, so maybe we need to use some combinatorics or some probability or permutation and combination, and then try to solve this problem. So since we are means we have two possible ways, either the indices will be even or odd. So like for even indices the digits must be even, this was the condition, and set of even digits is 5, so it means 0 to 5, so 5 choices, and here we have 4 choices. And also leading zeros are around, so at the start of the string we can have 0 as well, means this will not make a number as invalid, right? So hence 5 possible values. So now we need to determine like in n l length, means l length string, n l length string, how many odd and how many even positions are there, right? So we need to determine exactly how many indices are even and how many are odd. So for example, we can simply see if n is even, then the odd indices are n by 2 and the even indices are n by 2, and odd indices are also n by 2 only. And suppose if n is odd, then uh, even indices are n by 2 plus 1, right? And odd indices are n by 2 only. So we can reduce this to n plus 1 by 2 so that it satisfies both conditions. So our final result is uh, means even positions are n plus 1 by 2. We are doing plus 1 by 2 so that we do not need to calculate it separately for even and odd. And for number of odd positions is n by 2 only, right? So this we have find out. Now at each position, means there are these many positions of even digits and these many positions for odd digits. Now at each positions, how many choices do we have? So for this we have 5 choices, and for this we have 4 choices. And we can see that these choices are independent. Like the occurrence of 0 here does not means prevent the occurrence of 2, 3, 5 and 7 here, like the prime numbers. So whether whatever number gets put up here, it does not means hinders the occurrence of any other number here. Anyone can be present here. So hence the choices are independent. So as you can see, like choice of a digit at one index does not affect the choice of at another index. Hence these are independent events here. So hence we can like if we try to find out all the possible ways, we can just multiply the number of choices at each index, right? So what will be the total number of choices? So uh, we can see it in form of PMC. So here we have 5 choices, here 5, here 5. At all even positions we have 5 choices, and here we have 4 choices, 4 choices, 4 choices. And we'll just be multiplying all these possible ways to get the number of digit strings. And hence the number of times 5 will occur is 5 ki power, means choices for even pose, to power count of C even, which is n plus 1 by 2. And here it is 4. So it will be total equals to 5 ki power n plus 1 by 2 into 4 ki power n by 2. So this will be the result of for a given particular n. Now as we can see, like n can go up to 1e15, right? So this result can be very huge for like bigger values of n. So we are given that since the answer may be large, we can return it modulo 1e9 plus 7. This is a prime number which is generally given to take mod with it, so that a unique results exist for all means integer values which are greater than 1e9, right? So hence we cannot directly compute the powers here, like multiplying 5 n plus 1 by 2 times and multiplying 4 n by 2 times, because that will obviously take big of n complexity, and which is also not acceptable here, right? So now we need to do something, and also we need to find out the result taking model away. And here mod is 1e9 plus 7. So now we need to find out the modulo constraint. So here, for example, if we have the product of two numbers and we need to take it modulo with a particular mod, the result is, means this is a pre-derived formula. Like we can write it like this also: sigma mod into b percent mod and then the overall mod, right? So hence we can rewrite the above formula as 5 ki power n plus 1 by 2 percent mod into 4 ki power n by 2 percent mod and the overall mod. Why we are taking mod here? Because these values will be uh, very large. Hence we are taking it mod with 189 plus 7 so that it stays in the range of integer values. Alright. Now how do we compute this means x ki power p without means initially this big of n complexity is not allowed here. So how do we compute it efficiently? So there is a concept of binary exponentiation. You can maybe look it up, or I will explain you here only. So here the modulo means here we need to calculate 5 to the power n plus 1 by 2. So the value that we get means the integer value represented by n plus 1 by 2 will be representing it in the form of a binary representation. So for example, if we needed to calculate like x ki power 13, we'll write 13 in the form of binary. So it will be 13 would be 1011. Right? This is 13. Now at each step, this represents, since it is the 0th position, 2 ki power 0th position. So this represents x ki power 1, means x ki power 2 ki power 0 equals to x ki power 1. Then since this bit is unset, it will not represent anything. Here it will represent x ki power 2 ki power equals to x ki power 4. And here it will represent x ki power 2 ki power 3. That means x ki power 8. So overall, if we do like x ki power 8 into x ki power 4 into x ki power 1, then it will be simply x ki power 8 plus 4 plus 1, and that is x ki power 30. So hence if we convert like the number, the power in the form of a binary representation, then we can calculate this x ki power p only by iterating through the set bits of the given number, right? So that is what we generally do in uh, this binary exponentiation. So for example, initially if we wanted to calculate, for example, 5 ki power 13, right? So initially this 13 is broken as 8, means the binary representation is 1101, right? Now initially for this power we need to multiply it by 5 ki power 1, right? So initially the result would be 1. Now we'll be taking product to get the final result. Now if this bit is set, then that means, and we will take another variable like the current power that we have. So currently x is equals to 5. Okay. Now if this bit is set, then that means we need to account this in our result. So we will update result with result into x percent mod. And when we are doing this, when p is p means the last bit is set here, right? Now we move to this bit. How do we move to this bit? We'll just right shift p by one bit. Alright. So when we right shift p by one bit, the new p is 110. So we are doing the right shift so that we can get access to the rightmost bit in like just by taking it and with 1. Right. This like um, if a number is odd, p and 1 gives 1, and for even p and 1 will give 0. So this will allow us to check whether the last bit is set or not. Now if, and at each step, in here it represents 5 ki power 1, here it represents 5 ki power 2, here it represents 5 ki power 4, here it represents 5 ki power 8. So at each step we will be updating x with its double. So from 1 it went to 1 into 2, means 5 ki power 1 into 5 ki power 1. Then from 2 it went to 5 ki power 2 into 5 ki power 2. Right? And from 4 it went to 5 ki power 4 into 5 ki power 4. Then we got 5 ki power 8. Then we got 5 ki power 4. Right? So at each step we will be taking, means increasing x by multiplying it with itself and taking the right step. And while p is greater than 0, we do this thing. And the complexity here would be, since we only are traversing through the bits of p, and the maximum number of bits that can be in any number like is log of p. You should know like the maximum number of bits in any number is the logarithm of that particular number. So hence the complexity of this binary exponentiation is uh, big of log p only. Let's like show you the implementation of binary exponentiation so that you get the approach. So here we are doing the same only. We created a result variable which will be storing the final answer. Now while p is set, if the pth bit was set, like for example here p, the last bit is set, hence we update answer with, here it was 5 q power 1, so hence we multiply x to it, we will 1 into 5 q power 1, right? Now answer becomes this. And now when we move this side, we want 5 q power 2 here, right? Hence we multiply x by itself so that this 5 q power 1 becomes 5 q power 2. So now new x would be 5 q power 2, and answer is currently is 5, and p will be 110, right? Now since this bit is unset, will this thing will not get executed. Now x will become again get multiplied with this. So x will become 5 to power 4. Okay. And answer is still 5, and p will become 1 1 since we are taking right shift. Means this by 2 means we are moving it one step to the right, moving the bits one step to the right. Then since this bit is set here, so we'll update answer with answer into, so answer with answer into x, it will be 5 into 5 to power 4, right? And now again we will move p one step forward, and x multiply x with itself, so x will be 5 to power 8, answer will be 5 into 5 to power 4, and p is 1. Now since again this p bit is set, we'll uh, update answer with answer into x, so the answer will become 5 into 5 q power 4 into 5 q power 8. And as we can see, we have got the split that we wanted, like the binary representation 8 plus 4 plus 1 equals to 13, right? So this is the logic of binary exponentiation. And once we are able to do this in like this, we are calculating x to power p in big of log p complexity. And once we are able to do this, we will just apply the formula that we derived. We just need to find out 5 to power n plus 1 by 2 into 4 to power n by 2 and taking the overall mod, right? So this is what we'll do in the main code. We identify the total number of even places, which is n plus 1 by 2, total odd places is n by 2, so the total combination is 5 to power n plus 1 by 2 into 4 to power n by 2, and the taking the overall mod. So we just find out these values and take the power, find out the power, and we are using 1 LL, so that means since result is int, so this calculation is long, right? And we will take the overall mod and return the overall result. So the overall complexity of this solution would be big of log n, because the powers of means these even powers are n plus 1 by 2, and complexity of this is log p, log power. So let's try to submit the code here as well, and we'll see like how well it runs. So as we can see, like it beats 100% of the runtime, because the complexity is really fast. So I hope means you get the approach. If you didn't know about binary exponentiation, then you got to learn something new here. And if you have any doubts, then feel free to comment down. Thank you for watching.